Okay, so continuing, maybe another example. So C, suppose we had yi equals gamma 0, gamma 1, xi1 plus gamma 2, exp, say again, gamma 3, xi 3, 2, xi2. Maybe just that, plus epsilon I. Okay, so two predictors now. Two predictors and four. So two predictors and four parameters. Okay, this one's nonlinear, of course, too. I can't think of any transformation here that would make this linear. It looks almost linear, but this is a problem, right? And I can't take the log. Usually if you see an exponential, you think, I can maybe take the log and make a transformation, and then I'll have something that's in a linear form. But you can't do that here, right? Because you have these other sums, so there's no way to do it. So this is not linear. It's not intrinsically linear either. And so one thing we could do is, let's see. Yeah, so one thing to point out, so remark, the number of predictors, you see, is not tied to the number of coefficients anymore. It used to be that it was, one less? So yeah, there was one more parameter than there were predictors always. You'd have B0 through, say, B2. That meant you had two predictors, but you had three parameters. Here we see we could even have other gammas. So you could have a gamma in the power here or something. So you could have, 30 gammas and 6 predictors or whatever. So the number of predictors is no longer always one less than the number of parameters in NL. Okay. So we'll typically use Q. So notation. This is from the book. Notation. We'll use Q for the number of predictors and P minus 1 still for the number of parameters. Okay. So I better just check my notes to make sure that's how they did it. Yes, I think so. So notation, we'll let xi, now this is when we have multiple predictors, xi will be xi1, xi2, down to xiq. So we have q predictors. We'll also take out the 1 because here you do have a 1 here, but you don't always in nonlinear regression. So it doesn't really make sense to include the constant 1. All right, so that's the notation. So this will be Q predictors. Okay, and the gamma parameter vector will be gamma 0 to gamma P minus 1. So we'll still have P parameters, same as in linear. That's probably the way to remember it. The number of parameters is the same. Okay, so we'll just call it Q. Because it doesn't depend on P exactly. All right, well, then this is another one, right? What would Q be? 2 here, and P is 4. Okay, and there are more. So we could keep going with other examples. So maybe one more. We could have, say, something like, let's see, yi equals gamma 0, 1 plus gamma 1, exp, gamma 2, xi, plus epsilon I. Here the regression function is this. I could actually, if I take the log of this, I get log of this. But yeah, here I have a sum, and you would have screwed up this anyway. If you try to take the log of both sides, you will no longer have a normal error at the end. So this is nonlinear. These are both nonlinear, right? It's clear. So NL and NL. Only the first one was linear. Well, these are actually examples of pretty important ones. There were two pretty important ones. I just want to draw a couple of pictures. They had these two in the book too, and these are really common in simple models, maybe even a disease outbreak or something. You could see these. So you could have something like, here's one I have. So something goes from 20 to 100. I don't know, you can think of it as whatever you want. You can think of it as cases or whatever you want to think about this as. And I get something like this maybe, and it's supposed to be asymptotically sort of going to this. Now, it's not a very good picture. It was supposed to be more like this. And all I wanted to do is draw a picture on my screen. Okay, and this will be, let's say, E, Y, I. This is, well, let's just get rid of this. This is the regression function, right? EY. So I would just substitute in subscripts y, but you already used to the, we can take that out and just call it the regression function. Okay, so you see as x is down here, x gets bigger, this term goes to 0. So when I start, it's at 20 and it's increasing fast, it's exponential. But let's see, yeah, so this is like this, but then it's like this. Yeah, so it's increasing fast. It's a negative exponential reflected about the x-axis. So it's increasing fast at first, and then it starts decaying off because of this minus sign. It gives it that increase fast at first and then slow off. If this were positive, it begins slowly, right, and then accelerates. So this is called an exponential model. And there are a lot of them. This is just one of the simpler ones, but there are even simpler ones like exponential growth. Let's look at another one. Suppose we had EY, just the regression function. I'm writing it without the subscript. 200 over 2 plus 8 e to the minus x over 2. Sorry, I'm so sloppy. So this, I did it so it would also go from 20 to 100. But it does it a little differently. It starts off gradually this time, and it doesn't have that exponential start. And then it also, so maybe this is more like a disease outbreak, right? This is called a logistic model. Again, these are simple models with just one predictor. Okay, you can take elements of these functions and add other predictors and have a good time. Okay, what do we have to do? So I think what's next? So we're all set. We have this idea of we can make more complicated models. By the way, when you're looking at this, are you seeing points here? Now it's time to maybe see some points. Right here. Okay, so here's your data. And these model these. Now, could you take a line? Yeah, you could take a line through there. It might not be that bad, but you could see if it may truly really have this shape, okay? If you studied differential equations at all and things like that, you know, that a lot of natural phenomena makes sense. You could kind of see where these equations come from. But we're not going to do that at this point, this late in the game here. We're just going to say, okay, say this is the model. This is the regression function. So the full equation for the model here would be, if I want to think of these data points, yi equals ey, right? Yi equals 200, 2 plus 8 e to the minus xi over 2 plus ei here, where ei. Okay, and this is important for a lot of the inferences and for just understanding the fit, even just at a simple level of understanding the fit, to understand that this is, again, constant from not linear to nonlinear. This is the same. So, okay, so the next thing to do is fitting the model, okay? So we need to fit the model. Okay, so so just like we had betas for linear regression, we had to find little b's. We want to find little g's for the gammas. Okay, so that's where that comes from. And from the theory, if we accept that these are normal, the errors are normal and independent, the theory says that the least squares and the maximum likelihood estimators give you the same estimates, and there are good estimates too. That they're not always the best unbiased linear estimates. They're not generally unbiased, and they're not minimum variance. They're not even normally distributed, but they're still good, maybe the best you can reasonably get. So the approach will be to use either of those. So approach, use MLE. We're actually not going to use MLE, even though it's a little more powerful, or least squares. We'll use least squares. Both give the same estimate for gamma. Let's add the note, even though we're not going to do anything mathematically with it. G is not normally distributed, is biased, and I'm running out of ink, and does not have min variance, but is generally a good estimator. Okay, so I'm going to show you we get the same thing, show you how to get these. And it's important because even though you're going to use software to compute little g, just like you used LM to compute little b, it's important to understand even how to use the software. It's more complicated than LM. Okay, so that will be another lecture.